Okay, let's get started then. Good afternoon, everyone. Welcome back to the CAFNOR Research Council webinar series. Today is our fourth webinar of the spring semester, and we have Dr. Noel Aloysius, a faculty member in CAFNOR with a joint appointment in the College of Engineering as our speaker. Before I formally introduce Noel, I would like to say a few words about the CAFNOR Research Council, or CRC. We formalized CRC about 3 years ago as an advisory council that would provide advice to my office, that is the CAFNOR Office of Research. We do have faculty from every division represented on the council. We also have staff, graduate student, and postdoc representation. This webinar is an example of some of the activities of the council, in addition to providing advice to me. They also organize the annual CAFNOR Research Day, help make decisions regarding several research-related awards in CAFNOR, and funding opportunities from my office, like the Joy of Discovery Seed Grant Program and the recently announced Matching Assistantship Program. When they help make important decisions in the Office of Research, they are representing you. In other words, CRC plays an important role in shared governance in our college. With that, let me briefly introduce our speaker. Dr. Noel Aloysius is an assistant professor in the School of Natural Resources, jointly appointed also in the Department of Biomedical, Biological, and Chemical Engineering in the College of Engineering. Noel received his BS in Civil Engineering from Sri Lanka, MS in Earth System Science and Policy from the University of North Dakota, and PhD from Yale University. He completed postdoctoral training at The Ohio State University before joining Mizzou. His research and teaching focus on terrestrial hydrology, watershed biophysical processes, and environmental informatics. So without further ado, please join me in welcoming Noel. Noel, the floor is yours.
Thank you, Shibu. Let me. Okay, thank you all for the opportunity. I will try to present some of the research activities that we have been doing for the past few years, some of the ideas that we started developing, and some of the ongoing work that is relevant to the Mississippi River Basin and its land and natural resources management. I'll start by looking at some of the recent activities and events. Here we are looking at the 2019 flood that in the Missouri alone affected and caused an economic impact of close to $20 billion in terms of levee breach, flooding, and prevented agricultural farming activities. As a result of this recent extreme events, there has been a lot of interest in identifying best management practices to improve or reduce the risk of natural disasters affecting our economic activities. Some of that, as you can see in the recently passed budget, there is considerable funding allocated for flood damage reduction projects. On the other hand, the state with the use of the American Rescue Plan Act, there has been an allocation, as the governor has announced recently, of about $10.5 million to establish Missouri Hydrology Information Center. In addition to that, you might have heard about the newly established campus-wide Missouri Water Center. There has been a lot of activities as a result of these unified efforts to improve and increase our understanding of the challenges ahead in managing the Mississippi River Basin water resources. In this talk today, I will provide an overview of what are some of the challenges and what is going on within the Mississippi River Basin related to the environment, as well as multiple ecosystem services that are being provided, current research and opportunities for collaboration, then provide a few examples of education and training activities that we have been doing in my research group. So the overview of the research that I'm going to present today is, what we are doing in terms of developing computational tools related to water resources availability and management, and what kind of instrumentation activities that we have planned and established in order to understand various ecosystem states and fluxes, and how we are going to integrate this instrumentation with the computational tools. Those two are the focus of today's presentation. However, in addition to that, we are also collaborating with other faculty and experts at the university to look at institutional and stakeholder barriers for adoption of technologies and decision tools, as well as various training activities for our stakeholders, educators, and students. So if you look at the Mississippi River Basin, it is the third largest river basin in the world after the Amazon and the Congo River Basin, with a catchment area of 3.2 million square kilometers. It passes through or is part of 33 US states and 2 Canadian provinces. The extensive river training and hydraulic infrastructure that was established over the span of over 100 years for various activities, including navigation, flood control, irrigation, water supplies, recreation. As a result of this massive infrastructure development over the past over 100 years, there has been several thousands of small and larger dams, levees, and other river training work constructed by various federal agencies, including the US Army Corps of Engineers, Geological Survey, Department of Agriculture, Bureau of Reclamation, and various other state and federal agencies. In addition to that, there are a lot of private sector investment, for example, small reservoir construction for water supply by municipalities, as well as private sector people. As I mentioned, the ecosystem services include providing navigation, flood control, irrigation water management, and then providing water supplies and recreation. This infrastructure spans all the way from the northern states to the Gulf of Mexico. If we specifically look at the upper Missouri River system, as you can see, there are some large reservoir constructions, reservoirs operating mainly for flood control, hydropower, and navigation control. Most of the large reservoirs are located upstream of Omaha, Nebraska, which essentially control the river flow downstream of Omaha all the way to St. Louis, which has significant impact on how much water is available and accessible in the main Missouri River Basin. Some of the significance of these managing the river flows, I have highlighted them here. So one of the reasons to control this and regulate the upstream reservoirs is to make sure the downstream flows are sufficiently maintained for barge flow. One example here, the river depth has to be maintained at adequate levels in order to allow transportation of goods and other services through the river. One example is if every a 1-inch loss of water level in the Missouri River will result in about 500 tons of cargo not being able to move to the Gulf Coast, which will result in increased road and rail transportation, which can lead to congestion, and as a result of increased fuel use to transport this could result in increased air pollution. And as a result, the US Army Corps of Engineers, which manages most of this large-scale hydraulic infrastructure, requires or asks the Congress to mandate adequate flows, irrespective of other ecosystem requirements. On the other side of the on the Mississippi side of the river basin, there are large dams and locks that facilitate the movement of barge traffic all the way from St. Paul, Minneapolis in Minnesota, all the way to the Gulf Coast. As you can see, the elevation difference of close to 400 feet from upstream somewhere in Minnesota, in Minneapolis, all the way to the Gulf Coast, it has to be maintained such that the barge traffic can be easily led through. So in order to do that, there are several dams and locks, which requires continuous maintenance in order to facilitate the movement of goods upstream and downstream. As you can see, the inland transport system, it's about 11,000 miles long, with at least a 9 feet depth water to navigate to allow river transportation. On the whole, within the entire continental US, there are 186 locks that facilitate this transportation, moving over 600 million tons of cargo. The cost compared to rail and road traffic is substantially less, with a replacement cost of about $125 billion, right? So this massive infrastructure within the Mississippi River Basin requires careful planning and continuous management so that the economic drivers, economic activities can be sustainably managed. In addition to the dams and reservoirs, there are also a lot of levees constructed both by the federal government, state government, as well as private entities. Majority of the levee systems are federally owned and managed. However, there is substantial investment by other stakeholders. Overall, there are about 11 million people live and work in places that are protected by levees. There is substantial infrastructure that a levee failure can cause damages in terms of economic costs as well as people's lives. The barge transport alone, which I described, moves a lot of the value of barge transport, as you can see, with major grain crops that we produce within the Midwestern agriculture. It's about $400 billion on an annual basis, the amount of cargo that is moved through this barge transport. It also generates close to $100 million in fuel tax revenue, which are used to maintain several facilities. Close to 1 trillion property values are protected by levies. So this is a massive infrastructure that is prone to changing environmental conditions, particularly changing severe weather patterns. Shifting gears a bit, what are some of these economic activities? As you can see in this figure, the largest land and water management or appropriation activities are here: production of food, fuel, and other nature-based production. What you see in this figure, each red dot represents almost 10,000 acres of managed land. Nearly 2/3 of the entire Mississippi River Basin catchment area is somehow managed, whether it's for food production or by urban infrastructure. Now, as a result of this increased activities within this river basin, as you can see, the environmental cost at the downstream in the Gulf Coast as a result of increased hypoxic zone, which affect downstream ecosystem services such as fisheries and other activities. The way to look at, if you look at the large-scale infrastructure development within the Mississippi River Basin, has resulted in substantial reduction in sediment delivery to the Gulf Coast, which again affects the downstream ecosystem services and impact. There are several negative environmental impacts, including saltwater intrusion along the Gulf Coast. This change has happened over the past 100 years as a result of continuous expansion of hydraulic infrastructure to manage land and water resources. Another significant change that altered the landscape within the Mississippi River Basin is the increased subsurface drainage in order to make the agricultural activities productive and economically viable. That has accelerated the water flow within several landscapes, particularly within the Midwestern region, including most of our northern states, such as Illinois, Iowa, Nebraska, and Minnesota. Another significant environmental concern is the increased pollution loads that enters our waterways as well as the Gulf Coast. Here, I'm showing you the two largest sources of pollution that causes various negative environmental impacts: nitrogen and phosphorus. On an annual basis, there's about 1.6 million metric tons of nitrogen-based pollution that enters the Gulf Coast, about 160,000 metric tons of phosphorus. What are some of the impacts of that? I will get to that in a bit. But what are the sources of these two major elements? It's mostly food and fuel production systems, followed by urban and other activities. So as a result of this increased pollution load deliveries, there has been national as well as state level plans to reduce these loads by at least up to 45% over the next 20 years in order to improve the quality of our water resources. Some of the impacts that I mentioned include harmful algae blooms as a result of this nitrogen and phosphorus pollution entering our waterways. This algae blooms produces various toxins that can be harmful to aquatic life as well as humans. Now, what is the picture when you look at our state of Missouri? As you can see, there are several large rivers drain into or passes through our state, including the Missouri, Mississippi, and various other rivers such as the Platte, the Kansas River, and other large rivers as I have shown. Here, what I see is how much water passes through from upstream areas, as well as the amount of these two pollutants that I mentioned, nitrogen and phosphorus, from the northern part as well as the east and the west. Now, what are some of the consequences of that? As a result of this increased loading, our state is also responsible, or will have to spend more on additional conservation efforts in order to treat the excess pollution that passes through our state. So here, as a result of this increased loading that is coming through or passing through our state, we need increased collaboration in order to address and develop appropriate conservation plans to improve water quality within our state as well as within the entire Mississippi River Basin. Now, what are some of the activities that our research group is doing in order to improve and understand some of the causes and mechanisms, including severe weather impacts? So as I mentioned before my talk, the rest of the talk is mostly focusing on the first two activities. What are we doing? I try to show some of our area of focus. Obviously, the entire Mississippi River Basin is the focus of our research activities. In order to understand this massive water resource infrastructure, we look at some specific areas within the river basin that are closer to and that we can study in details, which include our own Hinkson Creek watershed, where most of the MU campus is located, as well as on a very smaller field scale, which is the Jefferson Farm and Garden that I have shown in the figure bottom right. So some of the field experiments and studies are going on at the entire Mississippi River Basin and the Hinkson Creek and some other local watersheds that we have easy access to. The work include lab experiments or instrumentation work to test various states and fluxes, including soil moisture and other parameters, field scale instrumentation to measure various water fluxes, including vegetation, water use, and soil moisture dynamics. Some of the other activities include integration of existing field as well as national instruments to understand at a spatial and temporal scale what's going on, and then use these tools to model and assess the rainfall runoff and chemical transport mechanisms. And once we develop these things, use these tools to make decisions or develop decision support tools. Some of the field scale instrumentation include, we have multiple instrumentation that are established at the Jefferson Farm and Garden in order to measure soil moisture, as well as vegetation water use, at finer timescales from 5 minutes to the entire growing season. We are also developing low-cost sensing tools, particularly to measure water quality parameters such as temperature, turbidity, and pH. Then we are also developing tools, framework to transmit these instrument measured parameters near real time so that they can be used in a near real-time decision making. Another site that we recently started instrumenting is the novelty site, Greenlee Research Center paired water study. This was established about 30 years ago, where we are restarting the instrumentation facility over there with the goal to integrate this in real time so that we can use these our university facilities to understand better about the watershed scale fluxes. The study at the novelty Greenlee site include looking at soil moisture dynamics as well as various water quality parameters under three different conservation plan, under two different conservation planning, agroforestry and grass buffers, how they help to improve soil health, at the same time improve water quality. Another interesting, infrastructure that we have, which is managed by our colleague, Professor Neil Fox, is the Mizu radar that is again located at the Jefferson Farm and Garden. As you can see in this figure, the blue circles shows the coverage of our Mizu radar, which covers about, which has a range of about 80 kilometers. As you can see, the major national radar stations are located in these three locations in closer to St. Louis, Kansas City, and Springfield. So our station here covers some of the areas that are not covered by the national, the radar stations that are managed federally. At the same time, you also see there are certain areas where we still have some gaps. So one of the projects that we are working together with Professor Fox's group is whether we can use these facilities to develop rainfall products that can be used in hydrological modeling, some finer scale rainfall prediction that can be used, for example, to predict flash floods within, say, Hinkson Creek watershed. So this is an ongoing activity. We will provide more information as we move forward. Now, what are some of the impacts that we see in terms of rainfall runoff and chemical transport processes? One of the things that we see, this is based on our analysis of the rainfall characteristics over the past 30 years. What we see here is the intense rainfall events are increasing at a faster rate than smaller rainfall events. That means more rain, more intense rain events are happening. If you look at at a daily time step, at a and the rates are increasing at a faster rate than the smaller rain events, which has impacts on how various other fluxes such as runoff events are happening. What is the state here? What is the situation here in the state of Missouri? What we see here is we don't see much changes when it comes to total rainfall. However, when you see the intensities here within our state, also we see an increased intensities over time. That is, more severe rainfall events are happening more frequently in the recent past. Now, what are the implications of that? As I mentioned, the severe rainfall events are increasing, which causes more severe increased extreme runoff events. And as a result, because the runoff events, the pollution transport is tightly coupled with increased runoff, we also see more pollution, particularly nitrate and phosphorus-based chemicals gets into the water more rapidly as a result of increasing precipitation. Now, how are we going to understand the spatial and temporal dynamics of that, which I will present within the next few slides? Our effort here is to look at the spatial variability in land use and land management, and then use that information along with other weather parameters to develop watershed scale simulation models to understand the rainfall runoff partitioning, as well as some of the chemical transport mechanisms. This is a generic framework that we are using, how rainfall is partitioned into various fluxes, including evaporation, transpiration, overland flow, groundwater recharge, as well as soil moisture dynamics within the root zone. If you look at on a bit more detailed look at the watershed scale model development, what our attempt is to look at different land management units, and use this information, how the land is managed or how the land is managed, and incorporate these management decisions as well as other aspects in a hydrological model to understand how these different land management issues, land management factors can be used in a model to evaluate the some of the impacts on ecosystem services. Again, just to give you an idea about how we are doing, starting from the smaller scale, divide the entire Mississippi River Basin into smaller watersheds, further divide them based on the land use and land management, as well as other factors such as soils and topography. I'll show you briefly about how what we did, what we have accomplished so far for the Mississippi River Basin. We have divided the entire Mississippi into 7 larger regions: Upper and Lower Mississippi, Arkansas, Upper and Lower Missouri River Basins, the Ohio, and the Tennessee. Each one is individually modeled and integrated so that the system is modeled as a single unit. In order to facilitate the computational burden, the reason for dividing this into 7 is to manage the computational aspect of it. The watershed, the entire region is divided into smaller watersheds that are less than HUC 12 watershed size, which is again less than 100 square kilometer watersheds. The entire Mississippi River Basin is divided into about 2 million hydrologic response unit, and each unit is simulated to understand the rainfall runoff dynamics and the chemical transport mechanisms at hourly and daily time steps from 1980 to present, using all the available data that we have assembled so far. There's also another variant that we developed. We also want to know what the available and accessible water resources within the state of Missouri. In order to do that, we defined another spatial unit, as you can see in this figure, that also considers the external inputs, which I mentioned at the beginning of this presentation. So this is the modeling activities. It's a work in progress. We have some results that we are trying to put together in order to understand both at national level within the Mississippi River Basin as well as at the state level. Now I'm going to move forward and show you some workforce development activities that we have been doing, then conclude the presentation with some final thoughts. Some of the activities, these are a few examples of what we are doing in our research group. These three graduate students that I have, they are working on a project to evaluate different methods to estimate potential vegetation water demand within the state of Missouri, and then characterize the uncertainties in estimation methods within different climate regions. I'll show you why this research is important in the next slide. What you see here on the left side is the potential vegetation water demand within our state, which varies from about 700 millimeters per year to about 1200 millimeters per year. As you can see, there is increased water demand in the lower latitudes compared to the upper latitudes. Now, this is the annual demand. Here we have the demand during the growing season from May through September, which again varies from about 400 millimeters to about 800 millimeters. Now, the next part is, how much of this demand is met by rainfall. So those are some of the work that students are going to do. However, what I want to highlight is what is on the right side of the figure. Now, the estimate on the left side is based on one estimation method that uses various climate variables. Now, the students looked at several other methods and then look at how they vary. Here, but on the right side, you see a comparison between two different methods, then by how much they vary in terms of estimation methods, right? So if you look at within most of the state of Missouri, the potential plant water estimates can be over or underestimated by up to about 10%. One example is if you are looking at in mid-Missouri, the potential demand during the growing season, let's say if it's about 600 millimeters during the growing season to successfully raise a crop, we could potentially, based on the method that we used, we could potentially overestimate it by 10%, right? Now, that has implications of related to, if we are irrigating, are we over applying water, thereby wasting energy resources? Things like that are important economic considerations. So the students are trying to understand how we can minimize the uncertainties in estimation methods so that reliable methods can be proposed. That is one aspect of it. And the other, one of my students, Sarah Thompson, who recently awarded is a recipient of the MISO 39 award. She has been studying at least two different aspects. One is using remote sensing tools to identify invasive species in state parks. So her goal is to develop methods so that we can efficiently allocate resources to improve our state parks operation. She's also interested in motivating future engineers and other natural resource scientists to take up STEM fields, right? So she's currently working on a project as a part of her engineering sustainability minor to develop a proposal that we can work in collaboration with school districts to develop programs that can inspire and motivate elementary and high school students in STEM fields. Another project that we are doing, I currently have about 4 undergraduates working on sensor development. Here, we have Joe and David developing a low-cost sensor to measure water depth, temperature, turbidity, and pH. So they have been working on this project for the past 6 weeks as a part of the Engineering Research Fellowship. They have successfully tested and calibrated two aspects, how we measure water depth and water temperature. They are continuing to working on improving this, and we hope to install these sensors in the field in the summer so that we can test their reliability and viability as a low-cost sensor mechanisms. Finally, another student, Veronica Fritz, who is graduating at the end of this semester. She was a recipient of the UDALF Scholarship for Outstanding Research in Environmental Studies. She worked with one of my PhD students to install soil moisture sensors and assess how they vary across under different land management practices. Some of the results are presented here. She actually gave a seminar at the European Geophysical Union meeting in last year. Now, as a result of her experience with water resources and environmental sensing, she has been selected for an internship where she plans to travel to Rwanda in the summer to work on an irrigation management project. To conclude, what are some of the key issues that we will be able to address as a result of these various research activities that I presented? We can look at how we can sustainably manage our agricultural systems, which are key drivers, key economic drivers. How can we understand the impacts of changing weather patterns on agricultural water management, preparing for extreme weather events, conservation planning? As I mentioned, we have plans to reduce the excessive pollution runoff into waterways. So, what kind of conservation is required? How are we going to do that? Evaluating erosion and water quality concerns as a result of changing weather patterns, then looking at filter and transport mechanisms of various contaminants. And as a result, whether these implementations can improve human health is another aspect that we just started to investigate. With that, I will stop and open, if there are any questions, I will be pleased to answer them. Thank you.
Great. Noel, thank you very much for an informative talk. And so we do have a little bit of time for questions. And so, well, if you have any questions, please feel free to post your questions in the Q&A box, not in the chat room, and I will repeat the questions and then Noel can answer them. Well, I don't see any questions at the moment, but Noel, let me start off with a simple question. The modeling work that you are doing must be of interest to a number of state and federal agencies. So please talk a little bit about your collaborations, or if not already existing, perhaps your planned collaborations with state and federal partners.
So currently, we have an existing some existing work with the Missouri Department of Natural Resources, where in some of the northern Missouri watersheds, we are developing watershed conservation plans that can be implemented in order to improve water quality. So that's an ongoing work. And as a result of this work, we also got the opportunity to get some information or some of the data that the Department of Natural Resources has been collecting over the past several decades, which will be used in our modeling activities to improve the predictive capabilities. That is with the state collaborators. We also had a project with the Missouri Department of Transportation to look at the pollinator habitat along the highway conservation areas. That resulted in a report where we identified various ways that we can increase pollinator habitat quality, which also resulted in being able for us to look at on the transportation aspect as well. So we have an ongoing collaboration at the state level. And at the federal level, we are working with the US Department of Agriculture. We recently signed an agreement with the Agricultural Research Service, a cooperative agreement which will last till 2025. There is an allocation in the federal budget that will support various projects within MU as well as the ARS unit. Currently, in the first year, that project is supporting faculty research, 13 faculty research, and it also supports 7 graduate students. That is with the ARS, and I also have established mostly voluntary collaborations with the US Geological Survey as well as the EPA.
All right, thank you, Noel. So I see some questions, but so let me ask this one in the chat room first, and then I have 2 questions in the Q&A box. So how will this research and work fit into the new hydrology center at MU? So I'm assuming that Zach is asking about the new water center.
Could you repeat that question?
So how will this research and work fit into the new, he said hydrology center, but I'm going to say the new Missouri Water Center?
All right, so so a lot of the faculty who are part of the some of the funding sources that I mentioned now are part of the core faculty within the Missouri Water Center, who will be contributing to various needs of the state. One example is, the project that I'm currently working on. We will be developing watershed conservation plans that the state can use to develop or implement appropriate conservation measures to improve water quality. On the state level, if I'm right, Zach, I think the Missouri Geological Survey is expanding its instrumentation work, particularly groundwater monitoring as well as soil moisture sensing. So those instrumentation work can be used in some of the modeling work that I just presented to validate our results or to improve the predictive capability of our models, so that whatever the predictions that we provide are more reliable, based on which decisions and policies can be made.
Okay, so let me read a question from the Q&A box. Sorry if I missed it, but have you incorporated ordinance or buffers in any models? Have you ever measured the effects of protecting riparian corridors at scale?
Thank you. That's a great question. So one of the objectives of the entire modeling effort is, first, we want to look at what's going on now in terms of land management practices, as well as existing conservation practices, including riparian forests, as well as filter strips and various other practices. NRCS has potentially identified about 36 different conservation plans that can be implemented under various different conditions, right? So some of the modeling efforts include incorporating those existing practices and scaling it up and see how they will reduce, for example, nitrate loading into streams. So that is one of the objectives. So we have done some work. I did not present the results. We have done some work for the Grand River Basin. We have done some work in the Hinkson Creek, and our goal is to learn from these smaller scale models, and as well as the example that I showed at the Greenlee experimental site. You know, we have a solid experiment that has been going on for the past 20, 25 years that shows definite benefits of conservation. So our goal is to expand that and then see, you know, how much conservation is needed, how many miles long of riparian forests are required in order to achieve that goal that is set by the Gulf Hypoxia Task Force to reduce the nitrate and phosphorus loading to the Gulf Coast by 40%. So that's one of the objectives.
Well, so I see another question again in the chat box. So that is, could a remote optical infrared imaging be used to measure the water level?
So there are, NASA and the European Space Agency has multiple satellite sensors that are being used to measure water depth, you know, and subsequently stream flow. Now, those applications are, you know, it's helpful if the river segment is large enough. So Mississippi main river or the Missouri main river or the Ohio River, we will be able to track and measure water depth or the extent changes. Whereas smaller streams like the Hinkson Creek, things like that, it's difficult. So we need to have more localized sensors in order to track the water movement. So it's kind of a mixed bag solution where, you know, larger systems, we have appropriate sensors at the ground as well as aerial sensors to measure, and at the local scale, we need to go for ground-based instrumentation.
Okay, thanks, Noel. I can see a comment from Zach again. And I think, you know, he was referring to the actual the Hydrologic Information Center that is proposed in the governor's budget when he was asking that question. Well, we also have the Missouri Water Center leaders on this call. I see Dan Cassidy and also Damon Hall. And so if they want to make any comments, feel free to do so. There was another question here that I've asked the person who asked that question for further clarification before I can bring that up to your attention, Noel. But I will ask another question while I wait for further clarification on that question. If I get it, I will then ask you that question. But here is another one in the Q&A box. Is the campus supercomputing being used at all?
Yes, we use it extensively. So for the hydrology research group, we have a dedicated server where most of my students have access to, and then at the same time, these large-scale models, we run them at the on the campus high-performance computing system. And recently, we are also going to have access to the USDA's high-performance computing system, which is called SciNet. I think it's based in Iowa State University. The advantage, I believe, once we have access is, you know, we will also would be able to, I hope, over time, we'll have some back-end access to some of the national water and other databases where, you know, we don't have to, we could near real-time access them and then run the models near real-time to make real-time predictions. So that is an advantage that we hope to use in the future. But at present, the HPC, MU's HPC facilities are being used. And then students are being trained to use that as well.
Okay, very good, very good. Well, I don't see any further clarification on this question, but I'm going to ask you this anyway, Noel. Maybe you can answer. So do you use Lewis and Clark? If so, how will the arrival of Hellbender affect your modeling work?
Well, I'm not sure I understand the question well. So
okay, that's all right. That's why I asked for more clarification, and I have not received. So if the person who asked the question, if he or she is still with us, please.
I would like to add a comment, probably to answer some of Zach's questions. So if you are thinking about, or if you are in need of any of these things, you know, yes, still in the development process of these models, but eventually we want to make it available for our stakeholders so that it can be used to make decisions. So if there are opportunities, or if there are things that you want to know, if there are information that you can share that could improve the model's predictive capabilities, you know, we are open to collaborations, not only Zach, but others in the audience as well.
Okay, very good. So we are running out of time. So let me thank Noel one more time for an informative talk and leading a lively discussion. So, and also thanks to all of you for attending today's webinar. Our next webinar will be on March 24th. That is next Thursday, same time at 3:30. We will have Dr. John Driver, a new faculty member in the Division of Animal Science, joining us. Again, thanks everyone. I'll see you next time.